Okay, there we go. Yeah, so welcome everyone. Today's speaker is Jean. So just a quick bio. So Jean is a PhD student at the Toyota Technological Institute of Chicago, TTIC. He's advised by Nathan Cerebro, and his research focuses on machine learning theory and decision making. And prior to grad school, he received his bachelor's degree at Princeton University in electrical engineering. So feel free to start now, Jean.
So thanks for inviting me to this. So today I'm going to be talking about this paper which appeared in NeurIPS last year. So it's with a few co-authors at MIT, Zoyu, Sasha, and Ayush, as well as my advisor, Nati. Let's jump right into it. I'm sure you're all here because you guys like reinforcement learning. So reinforcement learning has seen a lot of really impressive empirical success in a lot of many different application domains. And one thing that's really critical in these application domains is that we have some learning agent who is operating in some super large, like high-dimensional state space, and they have to be able to make good decisions and adapt to their environment. And so one question that kind of arises when we're in these super large state spaces is one of statistical efficiency. So we want to understand how many samples do we need and how should we go and collect these samples. So let me dive right into the formal setup. We're going to be working in the finite horizon Markov decision process. So here is a table of all the notation. I'm going to assume the state space is finite. So this is mostly for mathematical convenience. But everywhere in the talk, I'll mention if there's actually, it'll be clear if there's an actual explicit dependence on S or not. So we also have an action space A, as well as a probability transition kernel and a reward distribution. And there's also this problem horizon H and initial state distribution. So how this interaction with the MDP proceeds is that you have a learner and some MDP, and the learner first sees a state drawn from mu, and then for capital H steps, they will play some action and then get back the next state and a draw of the reward. So the goal of the learner is just to find some policy which maximizes this so-called value function, which is the expected cumulative reward of running this policy and the MDP. Cool. So in this talk, we'll consider two different models of interaction. The first one is this generative model. It's also called the simulator. In this case, the learner can submit any state action pair, and then they'll receive a draw of the next state and a draw of the reward. There's also this online interaction model, where the learner submits some policy and they get back a trajectory which is sampled by running the policy on the MDP. So the generative model is only easier than online interaction because if you have the generative model, you can simulate the online interaction. One critical difference is that the generative model allows you to do some kind of resetting. So if you explore some state, you can go back and reset to it and try out a bunch of different actions. But in online interaction, if you're really in this large state space setting, you might not ever see the same state more than once. Cool. So now we can come to the goal, which is pack reinforcement learning, which is just that you're given some policy class. So this is just a collection of mappings from states to actions. We want to understand how many samples we need in order to find a near optimal policy pi hat. That is one that satisfies this goal that with probability at least 1 minus delta, the value of pi hat is almost as good as the value of the best policy in the class. And we call this an agnostic guarantee because this policy class pi does not actually need to contain the optimal policy. And so let's use this to denote for a given algorithm and MDP how many samples it needs to collect. The goal in this work is to bound this minimax sample complexity, which is what the best algorithm over the worst MDP, how many samples they need to use. And I guess to sort of warm up, we can talk about these three existing upper bounds. And these three, like, they're really simple. So the first one is that you can get a sample complexity which scales linearly with the size of the policy class. And to do this, you'll just run each policy a bunch of times and then return the one with the best empirical value. Another class of algorithms has linear in state space and action space dependence. And this is accomplished by these standard tabular reinforcement learning algorithms. And then there's a third algorithm, which doesn't have an explicit dependence on the state space size, but now has an exponential dependence on the horizon. And this is accomplished by importance sampling. And let me go into importance sampling because it'll appear later in the talk. What importance sampling solves is it allows you to do some kind of simultaneous estimation of the values of a bunch of policies at the same time. And the idea is really simple. So we'll just collect a huge data set by executing actions like uniformly at random. And here I'm going to use this like squiggly arrow to denote a trajectory being consistent with some policy. And one can show that this estimator is an unbiased estimate of the value of the policy. And therefore, with enough samples, you can be assured that by returning the policy which has the best empirical value, it's close to, it solves the problem. And let me return to this once again. So really what we actually have is some kind of meta algorithm because we know these three quantities ahead of time. And we can actually just pick whichever one minimizes this an upper bound. And we've really made like no assumptions about the problem. And it turns out that since we've made really no assumptions, like we can't really do anything better. So there's this result which says that in the generative model, in the worst case, there is some policy class for which the sample complexity needs to scale with the minimum of these three terms. Okay. So you can think of this as like some kind of no free lunch result. But of course, like, we can often circumvent this no free lunch result. And there are two approaches to doing so. Yeah, Chava, do you have a question?
Yeah, is there an H missing from the last term, like the SA term?
Yes, yeah.
Okay.
So I wrote it this way in general, in the talk, I'm not going to be too concerned with polynomial factors in H.
Right. But this is a lower bound, so it's
yes. Yeah.
Like,
I guess like you'll see why like I didn't include the explicit factor of H when I
but like the result does have the H, you just like suppressing it now, or
what did you say?
This result that you're citing here, does it have the H there?
I'm
just curious.
In the results, I guess. So the construction for this is like some kind of like binary tree, right? And
okay.
If you like kind of set all the parameters such that these three quantities are all the same, then you get the bound.
And the question is whether you can do it such that the third quantity is actually SAH.
Yes, I mean, like, so for tabular, we know that you can get a like
yeah, you can separate
H,
to
right?
get that. Yeah.
Yeah.
Okay. Right. I mean, yeah. So what you want for results like this is that you have the coordinate of pi, you have A, you have S, you have H, and for every such value, if these are large enough, you can find an example with that many actions, that horizon, that number of policies in your policy class such that these bond holds, right?
Yes, yeah.
So that, I guess, like, that's
yeah,
the
so
question.
there's, I guess it's like, it's only saying there exists some setting of S, A, size of policy class, and H, such that this bound holds and is like tight.
Right. So we know for the tabular, the addition is the coordinate of the pi. But like, anyways, we can move on. It's like, I will look it up.
Yeah. So okay. So I guess like I was saying that there are two different approaches to this. So the first approach is something that has been like really popular in the past decade, which is that we'll make additional realizability assumptions on the MDP. In particular, there are like essentially two main classes of assumptions. So the first one is that you can assume that you have some value function class, which such that the Q function is like approximately realizable, or you can assume that you have some transition model or like MDP model class. And I guess one issue with this is that this is essentially some kind of structural assumption on reality. And it's not super clear why it should hold in real world RL settings. But I mean, nevertheless, it's like a very popular assumption, and it's led to a lot of like very interesting work. In this talk, I'm going to actually focus on a different sort of approach, which is trying to understand what sort of structural properties of the policy class enable us to do statistically efficient learning. And I would say this is probably more common in other areas of statistical learning theory. For example, in supervised learning, we know that like this notion of VC dimension characterizes the sample complexity of learning. And for many other settings, we actually have very tight like characterizations of when certain function classes are learnable or not. And so stated in this way, the question that we ask is whether there is some complexity measure which characterizes the sample complexity. That is, like, we can do agnostic reinforcement learning whenever this complexity measure is small. And it's important to know that this complexity measure is just on the policy class itself and doesn't depend on the MDP. And so here's a slide with our contributions. The first one is that we introduced this new complexity measure, which is called the spanning capacity. And for generative model, we show that the spanning capacity is necessary and sufficient for learning. However, in online reinforcement learning, we know that spanning capacity is necessary, but it's not sufficient. And we'll have to make some additional structural assumption. We identify a new structural assumption called the sunflower property, which enables efficient learning. Cool. So I guess the first thing is maybe I should tell you what the spanning capacity is. So I'll try to go through this with a lot of examples so that you get intuition for it. So for the discussion, we can let M be any fixed deterministic MDP. And first, we'll define this notion called reachability. So we'll say a state action pair is reachable by a policy class if there is some policy for which if you run the policy on M, the state action pair will lie on this trajectory. Okay. And now we can define cumulative reachability, which is just at a given layer H, how many state action pairs are reachable. So to illustrate this, I have a simple deterministic MDP with two actions. And let's say there are three policies that look like this. In this case, we can just count up the state action pairs and see and compute the cumulative reachability. So if you observe on the last layer, the cumulative reachability is actually only 2 because this policy and this policy go to the same state action pair, so we don't double count them. And now to define spanning capacity, what we're going to do is we're going to take the max over all deterministic MDPs, as well as the max over all layers H of this reachability condition.
Silly question. Cumulative reachability on this figure for H equals 2. Why is it 3?
Yeah, so there is this one, and then there is this one, and then there's this one. So these are all three distinct state action pairs.
Okay, so it's actually below that. Okay, yeah, got it. Like,
yeah.
All right, so for the next layer or whatnot. Okay.
Right.
I was misreading the figure.
Cool. Yeah, so I guess in this picture, like the state action pairs are just individual arrows.
I see.
But related to that, isn't the state that's reachable the same for both policies there? Like for pi 2 and pi 3 unless the arrows are different, but it's reaching the same state.
Yes, yeah. So you can define this quantity in terms of like the states that are reachable. It turns out like so you
it's
can get
SA
very
pairs.
similar results,
Right.
but you have like some explicit A dependence. But I guess like in what we did, we just defined it as state action pairs.
Yeah, I forgot about the A.
Yeah.
Thanks.
Cool. So let's go through some examples. So the first one is that if you have a small policy class, each policy can only visit a single state action pair in a given layer. And so trivially, you have the bound that the spanning capacity is upper bounded by the size of the policy class. Another trivial bound you can get is that this quantity just counts state action pairs. So it's upper bounded by the total number of state action pairs. And the last one is that if you consider this MDP, which is the full like tree with like such that at each state, each action leads to a unique different state, then the spanning capacity is bounded by A to the H. And so what we've just shown is that the spanning capacity is bounded by the minimum of these three terms. And you might wonder if it's actually equal. So actually, it can be substantially smaller. So here we have an example where the spanning capacity is much smaller. In this case, we have like the action state is binary. So there's a 0 action and a 1 action. And we consider policies which take the 1 action on a single unique state. In this case, you can show that the spanning capacity is linear in H, but the quantity on the previous slide can be exponential in H. And in the paper, we have many more examples of different policy classes, which illustrate that spanning capacity can be much smaller than this upper bound. One other intuition about the spanning capacity is that you can think of it as like a needle in a haystack, right? So imagine that in this MDP, we hit a reward of 1 at a single state action pair. In order to discover where the reward is, we would need a number of queries, which is like roughly the spanning capacity. And then there's also this connection to reachability and coverability. Some of you guys might know of this paper in 2022. And they define a similar notion of cumulative reachability, but they define it for general stochastic MDPs. So of course, the definition that we have doesn't make sense anymore. Instead, you can generalize it to this definition, where we sum up the state action pairs. We sum up the maximum occupancy measure under taken over the policy class. And in their paper, they show that this is equivalent to this notion called coverability. And this coverability might be familiar if you are familiar with offline reinforcement learning. And this has been like these notions of coverage have been studied in RL for like quite some time. So actually, you can show this kind of result, which says that the spanning capacity is actually the worst case cumulative reachability. So even over stochastic MDPs, the maximum of this is the spanning capacity. In other words, the MDP that witnesses reachability being large is actually a deterministic MDP. Cool. So now we can go to the results for the generative model. So this is, I guess, a good warm-up. The ideas are really quite simple here. For the generative model, we have this characterization, which shows that the sample complexity is both upper and lower bounded by the spanning capacity for any policy class. Oops. Sorry. Yeah. So and then there's a h times log pi gap between the upper and lower bounds. I guess if you're interested, we can maybe discuss it in a bit. But for now, let me just like tell you what the lower bound and upper bound are. For the lower bound, it's exactly this needle in a haystack intuition that I mentioned before. More formally, we can actually just embed a bandit instance into this MDP, into an MDP. So we'll let H star and M star be some MDP which witnesses the spanning capacity being large, and then we'll just embed a bandit problem at that given layer. And then in this case, in order to pull one arm, you need to like sample a state action pair, right? So you can just reduce it to bandit lower bounds. For the upper bound, we actually realized that there's a very old like classical algorithm called the trajectory tree algorithm that solves this problem. And the key insight is that for any stochastic MDP, you can think of it as like a distribution over deterministic MDPs. And in order to do policy evaluation, what you can do is just sample these deterministic MDPs and then do policy evaluation over the deterministic MDPs. So to illustrate this, you can imagine first you sample an initial state, and then you sample both the left and the right action, and then you keep going down. And the key observation is that you don't actually need to sample all A to the H transitions. You only need to sample the ones which there is some policy which would actually reach them on the given deterministic MDP. So you can kind of do it in like a lazy sort of way. And you can bound the size of the trajectory tree by H times the spanning capacity. And then afterwards, you can just do policy evaluation. In this case, like say you have some policy which takes this path, you'll just sum up the rewards along this path to get an estimate of the value of the policy for this deterministic MDP. Okay. And the last thing to note is that for this algorithm to work, we need to do a lot of resets. So it's not clear how to adapt it into the online setting. And so here's a summary. So the spanning capacity is necessary and sufficient for RL with the generative model up to this H times log pi factor. Yeah?
I wait for you to finish the
Oh. Yeah, are you going to ask about this log pi or?
No.
Oh, okay. Yeah, so that I guess that's the main takeaway. So I was going to move to the online model now, but if you have any questions, you can.
Yeah, before the online, so there is something in between the online and the generative model, the local access model. So would the result also hold for the local access model?
Yeah, so this algorithm only it only resets to states it's already seen before.
Okay, so it's actually for the local access setting.
But the lower bound holds more for this more general, like I guess, global access.
The generative,
yeah. Okay. So in general, we don't really in this case we don't really have like any distinction between the two in terms of these results.
Yeah, I'm like you can have everything for local access for good.
Cool. Yeah, so now we're going to move to the online setting. And so I guess like to kind of tell you the story about this. So since we know the online model is only harder than the generative model, the lower bound that we had before already carries over. So if we want to show that like spanning capacity is necessary and sufficient in the online setting, all we need to do is prove an upper bound. But the previous algorithm didn't work because the previous algorithm required us to do a lot of resetting. So actually, like we spent like I guess over a year on this because we thought like we were like almost sure that we could prove an upper bound for this setting, and then we realized that you can't actually do that. So we have the separation result, which shows that the spanning capacity by itself is not sufficient. So here's like an informal version of the theorem. So there is some policy class for which the spanning capacity is like bounded by 2 to the square root h. If you want to learn it up to accuracy 1 over 2 to the square root h, you need 2 to the h samples. So in particular, this rules out polynomial sample complexity, which is where we have polynomial in these parameters. All right. And so the takeaway here is that unlike in the generative model setting, the spanning capacity is not sufficient if you only have online access. So we need some additional assumptions. So in our work, we identify a new assumption or a new like structural property which enables like efficient learning. And we call it this sunflower property. And the sunflower property has 2 parameters, k and d. And if you assume the policy class has bounded spanning capacity, as well as the sunflower property, then you can get some polynomial in these parameters bound. So I guess don't really worry about like all the the specific term here. Like I'm pretty sure it's loose and can be further improved. But just to summarize, we have just to summarize the state of affairs, we have the following result, which is that if you have both spanning capacity and sunflower structure, then you have polynomial sample complexity. Our previous lower bound showed that if you don't have, if you only have this bounded spanning capacity, you cannot get polynomial sample complexity. You can also show the same thing for the sunflower structure. But we don't actually know that the sunflower structure is necessary. That is, for any policy class, you need to pay for something which is like k and d in a lower bound.
Some clarification questions for the first part. The results mentioned there were not for deterministic MDPs. You were just using the deterministic MDPs as a way of building up intuition, right?
Yes. Yeah. Yeah. You can equivalently think of all the results as like worst case coverability, I guess.
Right. So what happens if we have continuous state spaces and policy classes? Like we could mention LQRs, for example, where we definitely do have positive results for the nice policy class of linear policies.
Yes.
So what, like there, it seems that this metric is infinite.
Yes. So I guess like there are these results which say like for linear policy classes, in the worst case, you can't learn them. Like there's this Simon Dew paper, right?
Sure. Oh, okay. So I see. It's like I'm making a structural assumption.
Yeah, you're making a structural assumption on the value functions of the model class. Right?
So if you're not making structural assumptions, you're kind of stuck here.
Yes.
Whereas we know that, like, okay, there could be nice cases. Okay, got it.
Yeah.
And here you're making a different structural assumption. The difference there is that like that already applies for the generative setting. So already in a generative setting, we see that there could be policy classes which together with structural assumptions, which maybe is natural, maybe not natural, who knows?
Yeah.
Will give you
for like linear policy classes, even in the generative model, this
right. Yeah, that's very clear. Like no further assumptions. Yeah. Okay, got it. Yeah. I'm just
Right. Yeah. So I guess now I can. I didn't actually tell you about this sunflower property, so I'll try to do that now. So I guess as a warning, there's going to be like a lot of notation, but I'll try to walk you through it. And if you have any questions, like I think this is like probably it's more important for me to like accurately convey this than like to go into detail about like any of the proofs. So let me tell you this what the sunflower structure is. So the sunflower structure, there are two parts to it. There's like a petal part and a core. And first we'll define this petal. So let's consider some set of policies, which we'll call this like core set of policies. And the sort of high level intuition is that we want this core set of policies to cover like trajectories which are consistent with some other policy, right? So say you have some policy pi. We say that this policy pi is a petal, and it has some petal set S bar of the core if the following is true. So let's look at all the possible trajectories which are consistent with this policy pi. What we need to happen is that there are either two things that can happen. So there's either some policy in the core set which is also consistent with the trajectory, or there's some state in this trajectory, in this list of states, which belongs to this S bar set. So you can kind of think of this S bar as like some set of blocking states, such that if the trajectory passes through one of these blocking states, then we don't really care that it's covered. Okay. And then to define the sunflower property, we say the policy class is a sunflower with parameters k and d. If there exists a core set, which is size k, and every policy in the original class has a petal set for some set of states, which is also bounded by d. Okay, and I guess here's a nice little picture. I think Ayush made this.
Looks like
so,
a sunflower.
What?
Looks like a sunflower for sure.
Yeah. Yeah. So.
Yeah, but I was still parsing the first part.
Oh, sorry.
When you move to the second, the sunflower part. So I don't know. So we say that policy class pi is KD sunflower. So K is going to be the size of this core.
Yes.
And D is going to be the size of the petal, like the states. So it kind of like this brings in both policies and states somehow, and that's how you're breaking out of the impossibilities.
Yes. I think the next slide, so I'll discuss in the next slide a bit more about this relationship between K and D. So you can kind of think of these as kind of trading off between each other, right? So like if you have a large set of core policies, then you can cover a lot of trajectories, right? And therefore, like the policies need to have can have smaller petal sets, right? Because the petal sets kind of control the trajectories which you don't care about covering. And the converse is also true, right? So like if you have a lot of petal states, then the number of trajectories that you need to cover is much smaller, so you can afford to have smaller k. So I guess something that's illustrative is if we think about like what happens if k or d is 0.
By the way, so now are we back to deterministic MDPs? Is this compatibility of trajectories, or are we worried about tiny probabilities? Like, how is this compatibility of trajectories even defined?
So this is a worst case assumption, and this holds for any trajectory, right? So we don't have any
meaning of that a trajectory is compatible with a policy.
Yeah. So this is just a sequence of states and actions, which is consistent with a policy, right? So
which
this
means
is the worst
that
case.
no zero probability transitions happen and no zero probability actions are taken. But
so there's
no arbitrarily close to 0.
So there's no probabilities here. There's no MDP so far, right?
So then what's the consistency? Well,
What?
policy is deterministic.
Yes.
Okay. And so this is only a restriction of on what actions are taken in what states?
Yes. Yes. Exactly.
Okay.
Yeah, it's
Okay.
just a
I
sequence
kind
of
of
states
get
and
that.
actions.
Okay. All right. And is that going to be an extension of this to stochastic policies, or that would be like outside of scope? Anything what you
We
said.
don't know how to. We don't know exactly how to extend our results to stochastic policies.
And
So
already the previous results have this issue?
for the generative model, I think so, because we're really working with like deterministic trees, right? So
yeah, okay. So I guess I just really missed this,
yes.
but good. No, figure we figured
Yeah.
it out. Okay, good.
Yeah, so the MDP can be stochastic, but the policy class has deterministic policies.
Yeah, got it.
Yeah. So I guess if you think about this trade-off between K and D, one thing we can think about is like, what happens if one of these is 0? So let's imagine like if we have D is equal to 0. In this case, we need to cover every single possible trajectory. And one way we can do this is like if we use either this idea of just A to the H unique like sequences of actions, or like we just use all of the policies. So that gives us this point on this graph. Another choice is if we just let every state be a pedal state. In this case, we don't actually need any core policies. So okay, so here I wrote it like K is equal to 0. Like if you notice in our result, if K is equal to 0, the sample complexity is 0. So there's like, I guess, a slight technical issue that K needs to be like non-empty, or K needs to be like at least 1.
Yeah.
But yeah, so like, I mean, you can essentially think of like this, if every set is a pedal set, then you don't need to be super smart with your designing the core set. And I guess that corresponds to this point. And you can think about this like kind of Pareto frontier of valid K and D for a given policy class. So it might look something like this. The curve might look different. And I guess one observation to note is that for these points on the axes, we already have algorithms that solve RL for them. So on the point on the y-axis, this is accomplished by like these tabular algorithms, and the point here we have like these importance sampling, or just try out each policy one by one, right? So I guess in some sense, like this K and D kind of can characterize this like Pareto frontier of what we can do algorithmically. So note that like the point on this y-axis and the point on this x-axis are very different algorithmically, right? So on the y-axis, these tabular algorithms are like really adaptive, right? So you might just like collect one trajectory from some policy, and then you look at your data, you do some like optimism or exploration or whatever, and then you collect a new trajectory, right? Whereas over here, these algorithms were like extremely non-adaptive. You just collected a huge data set and then use that huge data set to do offline like evaluation. So in order to get something in the middle, you need to combine both of these sort of ideas. And that's exactly what our algorithm does. So we can solve this RL problem for every point along this curve, right? So I guess like if you can think about it this way, that if you're given some policy class, and you don't care about computation, what you can do is try to find the minimum K and D that like minimizes the upper bound that we have, and then run the algorithm with that choice of core set and pedal set. Okay. So I guess how much time do I have left? Like 5 minutes.
Oh, you got like 10, 15.
Okay. Yeah, so maybe I can sketch the upper bound, and then we'll see where we are. So the upper bound relies on this idea of importance sampling. So recall this is what we did for importance sampling. You can like generalize it in this way: sample from some distribution Q, and one natural question is like, can we get estimates which are lower in variance, right? So before, the variance was on the order of A to the H, which is why we had to pay for A to the H in the sample complexity. But if we could actually get lower variance estimates, then we would be good to go. So one idea is that you can just try to sample from this distribution, which is uniform over the core set. Okay. And so if we try this, this is not actually going to work. And the reason why is because there is some missing data issue, right? So this estimate could be potentially biased because the policy that we want to evaluate could have generated trajectories in this MDP that no policy PyCore can. So we're missing out on evaluating those trajectories. So this wasn't a problem when we had the exploration set be uniform over all all A to the H policies. But if you go back to our assumption, it turns out that the bias is exactly due to these trajectories that pass through these states. But the bias, I mean, it still could be very large, but we know that it's always going to be due to the trajectories that pass through these states. And now we have to figure out how to control the bias. And at first glance, this might be impossible, right? Because each one of these petal states, each one of these policies has a different petal set, and the total number of these petal states could be linear in the size of the policy class, right? However, you actually realize that you only need to care about the petal states which are significantly reachable. They're reachable with probability at least epsilon. And so we only need to care about this set S epsilon. And if there are trajectories which pass through petal states which are not reachable with probability at least epsilon, you can control the bias. You can show that the bias is like linear in epsilon, or linear in d times epsilon. And the last observation we can make is that this set S epsilon is actually not that big. So this set S epsilon can be bounded by the spanning capacity over epsilon. And so this gives us our algorithm. So I won't include the pseudocode because it's kind of messy. But let me just pictorially or graphically tell you what's going on. So the algorithm has two steps. So there's an exploration phase and an evaluation phase. In the exploration phase, we're going to kickstart it by just sampling according from this uniform over this core set. And then what we're going to do is we're going to enter into this loop. And in each round of the loop, we're going to identify some new state, which is in this S epsilon set. And then once we've identified that there is some state like this, we're going to collect a new data set from that state. And to do that, we're going to run this pi plus until we hit S epsilon and then restart with this uniform exploration. And since we know that S plus is reachable by pi plus with probability at least epsilon, we know that if we run pi plus, it's very likely to hit S plus. And therefore, the total number of trajectories we need to do in this round is not too big. And then so we're just going to keep going in a loop. Eventually, we'll figure out that we don't need to discover any more states. And then we'll move to evaluation, which is now that we have all of these data sets, we're going to estimate all of the values and return the empirical maximizer. And so for these two orange steps, like the sort of way we analyze them is using something called this Markov reward process. Essentially, what we're doing is that the original MDP could have like a super large state space, but we're going to reduce it into like a tabular Markov reward process with state space which is bounded by S pi, bounded by D. And once we have a tabular setting, we can just do dynamic programming to estimate its value. Okay. So I have one more slide on the Markov reward process, but maybe I'll skip it for now. But I guess the main intuition was basically what I said before. Let me say a few words about the lower bound. The idea of this lower bound is that you want to design some sort of MDP, and a policy class, such that like learning or exploring in one part of the MDP doesn't reveal a lot to you in other parts. And we have to leverage this fact that we only have online interactions, so there has to be like a very large state space. So the intuition is that like we construct this like class of policies, and this policy class has like bounded spanning capacity. But we construct like a family of MDPs using this such that and each one is parameterized by some pi star and a decoding function. Let me, So I guess like the high level overview of this lower bound is that we have like a uniform distribution over a bunch of combination locks. And what will happen is that if you try to learn in this lower bound, you'll see one combination lock, but you don't actually get much information from it about what pi star is, because if you only see one combination lock, it's very likely that you'll never actually see the high reward. And in that case, you don't learn much about it. And then since you don't have this reset, you can never go back and explore the same combination lock over and over again, right? So basically what will happen is that the best thing that you can do is just try out the policies one by one. Cool. So so let me just summarize the results that we have. So what we do in this paper is we study this problem of agnostic pack reinforcement learning, and we identify this complexity measure called the spanning capacity. And the spanning capacity is a complexity measure that only depends on this policy class and not on the specific MDP dynamics. So we don't make any assumptions on realizability at all. And for the generative model, the spanning capacity we show is necessary and sufficient for learning. But for online RL, it's necessary but not sufficient. And we need to make some additional sunflower property that enables efficient learning. But our work still leaves open like what is the right complexity measure for online RL. We think that the sunflower property or some version of it is necessary, but we were not able to show that. And let me also briefly highlight a few other results in the paper. So one of them is like we do some extension to infinite policy classes using like Natarajan dimension, which is a multi-class variant of VC dimension. We have some connections to other sort of complexity measures. So you can show that the spanning capacity is lower bounded by some version of this something called the star number and the threshold dimension. And these are two quantities which appear in other parts of learning theory. And we also have some results on understanding like when you can improve these bounds with expert feedback. Yeah. So cool. So that's it for my talk. So yeah, let me know if you have any questions.
All right, great. Thank you.
Thank you.
So, David,
Hi, I was curious to know when you do. No, excuse me. Hear me?
Yeah.
Okay.
Yes.
When you do the bound on the set of relevant states, you do like the number. Excuse me. Yeah, at the before. Okay. Yeah. It's
Here?
related to this regret because I was wondering what was the impact on the epsilon. Because you do like, excuse me.
Yes.
Mm,
Yeah. So
yeah,
we have this epsilon to the fourth dependence. The way this arises is because we have like, sorry, we're going here, right? So this set S epsilon, we have like one like C pi spanning capacity over epsilon here. So there's it turns out that you need like yeah, so you have to control the ones with epsilon probability. And then so in data, when we do data collection, since this set is of set, like size C pi over epsilon, you need additional factor of epsilon there.
okay. Yeah. That's what I was trying to ask. Thank you.
Yes.
good. Other questions? Do you have some? So, yeah. So one thing that came to mind as you were showing the last slide is this extension to infinite policy classes. So where did you use at all that the policy class was finite? Like other than enumerating in the algorithms, right?
It's because our bounds depend on log pi.
Oh, okay. So those were kind of hidden somewhere.
Yeah. So
Maybe it was there, but I just didn't see
let
that.
me go here. So yeah. So okay. So this upper bound is like depends on. Okay. So there's an extra factor of h, whatever. But the upper bound has this log pi dependence.
Yeah, it's like a union bound kind of thing.
Yes, yeah, and you can't like remove this log pi, right? Because like if you think about bandits, like contextual bandits, like even yeah. So contextual bandits, this spanning capacity is a, where a is the number of actions, right? And you need this log pi when you're doing contextual bandits, right?
Okay.
But I like. So in this asterisk down here, I say that you can get results for infinite policy classes. So you can replace this log pi with like Natarajan dimension or something. Or essentially just like VC dimension if your actions set is binary. You can also get like something like that to appear in the lower bound. In the lower bound, it only appears, I mean, when I tried, it only appears additively. So you get spanning capacity plus log pi or VC or something.
Right. So that's a suboptimality potentially of the upper bound.
Yeah. So so the upper bound is a product and the lower bound is a sum of the two.
Yeah. Probably should be a sum.
Right. Yeah. So you can think of this like this these as like two separate sort of terms, right? So this spanning capacity is kind of characterizing like the complexity of exploration in some sense. Whereas this log pi is like kind of the complexity of doing some kind of supervised or statistical learning.
Yeah. Right? Got it. Okay. So when you were talking about the sunflower property, it's somehow this with the core set and like or core set up policies and uniform expression. Somehow policy covers came to mind. It kind of feels
Yeah.
like that you have the same thing, that, except that you need to notice that you can't really have it.
Yes.
Then you have the states that are left out, and that you need to deal with them.
Yes. Yeah. So when we were working on this, we were thinking about like policy covers. I guess the sort of difference is that like at least okay in what I'm familiar with policy covers, they're like trying to cover like these occupancy measures, right? So you want to set up policies such that you can reach all of the states which are reachable, right? But in our case, like we have to do something a bit more, which is that we have to cover like trajectory at the trajectory level, or at least like partial trajectories, right? So
Right.
So it's like it's I guess more clear when you look at this Markov reward process, where for each one of these transitions, to estimate these transitions, we have to do importance sampling, and so we have to cover things at this trajectory level. So we have to, yeah. But I guess we didn't really. It's not really clear whether this like policy cover is like how relevant it is, because in this case, since like we don't really have any assumptions on like reliability or something. It seems like really the only tool that we have is importance sampling, right? So importance sampling requires things to be covered at the trajectory level.
Very cool. Did you give any thought? I'm sorry.
I was just gonna say maybe we'll stop recording here.
Okay.